This map shows a 700-kilometer fault line stretching along Japan's Pacific coastline, down to the island of Kyushu. This boundary is the Nankai Trough. Here, the Philippine Sea Plate is actively subducting beneath the Eurasian Plate, grinding downward and building immense tectonic stress. Accumulated friction locks the plates in place until they violently snap, generating megathrust earthquakes every 90 to 150 years. Seismologists estimate a 70 to 80% probability of an extreme magnitude 8.0 or higher rupture occurring in the near future. The Nankai Trough functions as a predictable geological machine, one poised to strike Japan's most densely populated industrial and residential corridor. The last times this fault gave way were in 1944 and 1946. The kinetic force sheared steel railways and flattened traditional infrastructure across western Japan. Today, the population density along that coast has multiplied. Government modeling estimates that a worst-case modern rupture could result in nearly 300,000 direct fatalities. The financial destruction would approach 292 trillion yen, roughly half of Japan's GDP, driven by massive structural collapse and simultaneous nationwide supply chain outages. Surviving an event of this magnitude requires moving beyond standard disaster preparedness. It demands a highly engineered national defense architecture. Mitigating this threat requires a unified defense architecture, linking undersea telemetry and structural engineering directly to the civil logistics of the mainland. To build that defense, we first have to map the failure modes of the fault. This is a 3D model of the subduction interface. Geologically, the trough is divided into 5 distinct operational segments, labeled A through E. Subduction mechanics allow for 3 distinct ways this fault can fail. The first is a uniplex, or piecemeal rupture, where individual segments slip independently of the others. The second, and far more complex mode, is a paired sequenced rupture. Here, a partial break in one section transfers stress down the line, triggering a secondary rupture hours or even years later. During the 1854 events, the eastern segments ruptured exactly 32 hours before the western segments. In the 1940s, that delay stretched to 2 entire years. Finally, there is the absolute worst-case scenario, a simultaneous megathrust rupture. All 5 segments fail synchronously, compounding their energy release into a single magnitude 9.0 or higher event. An effective defense architecture must account for all 3 variables. It must be capable of surviving an initial shock and immediately preparing for unpredictable cascading sequence ruptures across multiple geographic domains. When the fault slips, the immediate threat transfers to the coastline. Coastal areas like Kochi and Wakayama prefectures feature deeply jagged mountainous inlets. This creates what is known as narrow bay bathymetry. This animation demonstrates the hydrodynamic effect. As a deep ocean wave enters the shallowing, narrowing bay, the massive volume of water compresses horizontally. With nowhere else to go, the energy forces the water column violently upward. Through this compression, rapid inundation tsunamis generated by the Nankai Trough are projected to reach extreme heights of up to 34 meters. Proximity compounds the danger. For these specific coastlines, the initial wave arrival will strike just 2 to 5 minutes after the shaking stops. The mathematics of this bathymetry completely eliminate traditional evacuation timelines. Mitigation here cannot rely on distant inland retreats. It must depend on automated barriers and hyper-local vertical structures engineered right on the shoreline. Hundreds of kilometers away from the epicenter, the threat profile changes. The deep sedimentary basins that house Tokyo, Nagoya, and Osaka face a highly specific vulnerability. The immense fault slip of the Nankai Trough generates long-period ground motion. As high-frequency seismic waves hit the deep sediment of these urban basins, they instantly stretch out into long, rolling, low-frequency waves. These elongated waves create resonance periods of 2 to 10 seconds. When they interact with the flexible foundations of modern skyscrapers, they act as an amplifier, forcing the upper floors into a severe, wide-arc sway. This swaying motion can last for up to 10 unbroken minutes. While the buildings themselves will not collapse, the violent whipping action snaps utility risers, destroys structural fittings, and permanently disables elevator shafts across the phi line. The Nankai rupture load does not dissipate harmlessly into the distance. It systematically hunts for the specific resonant vulnerabilities of Japan's most critical economic hubs. Defending against these combined threats starts at the bottom of the ocean. Japan has deployed the DONET and NNET seafloor observation networks directly along the subduction zone. These cable-connected arrays use hydrostatic pressure sensors to detect the physical generation of a tsunami wave right at the subduction interface. This captures telemetry tens of minutes before the wave ever reaches a coastal tide gauge. That deep ocean telemetry feeds instantly into the Japan Meteorological Agency. If anomalous slip or a partial rupture is detected, it triggers the Nankai Trough Extra Information Protocol, issuing nationwide public advisories within 2 hours. On land, early warning is paired with rigid engineering. Nationwide residential earthquake resistance has now reached 90%, and critical public facilities have been systematically retrofitted to withstand maximum Shindo 7 shaking. Along the shoreline, automated sea gates are designed to seal river mouths within minutes, while heavily reinforced coastal walls stand ready to absorb the hydraulic shock of the incoming surge. The deep ocean telemetry buys critical minutes, and the structural defenses will absorb the initial kinetic load. However, no amount of concrete or early warning can prevent the massive logistical collapse that follows. The first major failure point in the aftermath will be geographical isolation. Instantaneous structural landslips and coastal road destruction will effectively sever the Izu, Ki, and Muroto peninsulas, cutting them off entirely from ground-based rescue operations. Search and rescue teams attempting to enter via heavy-lift helicopters or amphibious ships will face immediate secondary hazards, particularly massive urban fires ignited by severed gas mains. Because of the paired sequence dynamics, these responders will be working inside a damaged segment while facing the unpredictable, lethal threat of adjacent locked segments rupturing violently mid-rescue. Between the simultaneous disruption across 31 prefectures and massive geographic isolation, centralized government rescue and supply chains will effectively cease to exist for millions of residents. Because the national logistics grid will be paralyzed, the standard 3-day emergency stockpile is mathematically inadequate for a Nankai rupture. Citizens must prepare to execute the 14-day rule, a strict requirement of at least 2 weeks of absolute self-sufficiency. This mandates specific hardware. High-capacity alternative power stations are required to keep medical and communication devices running. Because municipal sewage networks will inevitably collapse, chemical polymer toilets become a strict necessity to prevent secondary disease outbreaks. This leads to a final, human-centric protocol known as Tsunami Tendenko, a survival philosophy derived from centuries of coastal disasters. The protocol is rigid. When the shaking stops, bypass central instructions, do not waste time searching for relatives, and evacuate independently to high ground or vertical towers immediately. The combination of real-time seafloor telemetry and reinforced seawalls provides a vital buffer, but against a 5-minute tsunami arrival window, survival ultimately rests on immediate, independent action.